Welcome to part B of chapter 4, chemical reaction and chemical quantities. I do have two sections in part B to wrap up chapter 4. Allow me to share my screen and we will get started. And these are the two sections I would like to cover in part B. 4.4 stoichiometric relationship, we will look at the limiting reagent concept, theoretical yield, and how to calculate the percent yield in a chemical reaction. And we will look at specific types of reaction. The text only covers combustion reaction, alkali metals reaction, and halogens. We have only three types of reaction. However, I'll recommend that you learn other types of reaction, decomposition reaction, single replacement reaction, double replacement reaction, precipitation, acid-base neutralization, and of course, we will talk about the redox reaction. Let's see part P on the lecture presentation 4.4, the limiting reagent concept. Recall our recipe for pizza, where to make one pizza, you will need 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese to make one pizza. Suppose we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce. How many pizzas can we make? Using the dimensional analysis and the ratio, we assume this is a balanced chemical equation. Crunching the numbers, it turns out that the least number of pizzas we can make out of the ingredient given here is 3 pizzas. We call this the theoretical amount of pizza we can make out of the given ingredient. The rest are called excess reactant if it was a chemical reaction. The reagent in a chemical reaction, the reactant in a chemical reaction, which limits the amount of the desired product, is called the limiting reagent or limiting reactant. You need to understand what a limiting reagent is, and there is no way you can just look at the balanced equation and say, this is my limiting reagent. You need to do the calculation and see which one gives you least amount of the desired product. Here at the recipe, we started with 15 cups or 15 ounces of tomato sauce, 10 cups of cheese. For crust, you see the one which gives us least amount of the desired product is called the limiting reagent or the limiting reactant. The other one or the rest is called excess reagent. In this case, excess reagent will be the tomato sauce, and the other one is just a limiting reagent. Theoretical yield is the amount you expect to, the theoretical amount you expect to produce from the limiting reagent. In this case, tomato sauce is the limiting reactant, the reactant that makes the least amount of the desired product. Don't look at the number of molecules present and say this one is present in small amount and therefore it is my limiting reagent. No, it doesn't work like that. In some cases, you may have a reactant which is present in large amount in terms of moles will turn out to be the limiting reagent. So the only way you can figure it out is to calculate the theoretical yield using the stoichiometry, and whichever gives you the least amount of the desired product is the limiting reagent. And the amount you expect from there is called theoretical yield, okay? So in our example, the maximum number of pizzas we can make depends on the ingredient. This is the tomato sauce. We call this theoretical yield. Theoretical yield is the amount of the desired product that can be made from a chemical reaction. And here, underline the word chemical reaction because there is the balanced equation in there which will determine how much of the desired product will be produced. In this case, theoretical yield. Percent yield is determined using the actual. This is what you will actually make. Let's say, for example, if something happened, maybe we pan one of the pizza and we remain with with two, we expect to get what? 3 pizzas. But let's say we burn one we just toss it off the dust bin or throw it away on the trash can. So we end up with 2 instead of 3. We call the 2 which will end up with actual yield. So assuming that while making pizza, we burn 1, right? We drop by 1 and the 2 remain. To calculate the percent yield, right here, it is the actual over theoretical times 100. I know you know this equation. Percent yield of any reaction is the actual will be at the top over the theoretical, and theoretical you calculate from the limiting reagent and the balanced equation times 100. So in this case, it's 67% yield because one of them just got burned. You need to be able to calculate the theoretical yield, calculate the percent yield from a chemical reaction. Sometimes you may be asked, what will be the leftover from the excess reagent? It will take time to really to navigate the problem based on the stoichiometry, right? And the amount of each reagent in a chemical reaction. So understand what a limiting reagent is and the excess reagent. Maybe just calculating one or showing you an example on how to proceed with the theoretical yield, actual yield, and percent yield in a reaction. This is a balanced equation between reaction of methane with oxygen to produce CO2 and gaseous H2O. This we balanced earlier on. So from our balanced equation, this is how it looks like. Suppose we have 5 molecules of methane and 8 molecules of oxygen gas. Which one is the limiting reagent? You have to look, you can use any of the product to determine which one is the limiting reagent. But here we have specified that calculate the number of moles of CO2. But if you are asked which one is the limiting reagent, without specifying which reactant in particular, you can use any of these products to figure it out, the limiting reagent. So in terms of moles, we expect to have 5 moles of what? 5 moles of CO2. It is 1 to 1. So 5, 5. If you have 2, you have 2. Let's see for oxygen, so it's 8 to 1, so 4. If you look at how many will be consumed, all 8 will be consumed. Since oxygen is the limiting reagent, all 8 will be consumed, producing 4 molecules or 4 moles of CO2. If you see it's methane is in excess, it will be our excess reactant, and if 4 will be consumed, if you are asked to calculate the limiting reagent, we need to subtract how much will it remain. So if we consume 4, all right, if 4 will be produced here, we started with 5, 1 to 1. If 4 will be produced, that means we'll use 4 out of the 5, and 1 will remain as excess reagent. Here is an example on mass to mass. If you are given the masses of each reactant, you need to figure it out which one is the limiting reagent by converting the given masses to moles and then use the mole ratio to figure out the maximum amount or the theoretical yield of the desired product. Here is magnesium metal. This is the mass of magnesium. Oxygen gas. This is the mass of oxygen. Here you see mass to mass, all the way starting with the mass of magnesium oxide. Throughout this route, we will do mass to mass, mole to mole. So initially, we'll have to convert the mass of magnesium to moles of magnesium using its molar mass. You have to use the periodic table. This is the mole or molar mass of magnesium of the periodic table, number of moles. And then the mole ratio here is between magnesium and oxygen. Remember how to set it up so that you cancel moles of magnesium, and then mole ratio, or using the molar mass rather. Once you have the moles of magnesium oxide, you use its molar mass. Here you have to calculate if you are not given, all right? The molar mass of magnesium plus oxygen, 40.31. So you need to use the periodic table. This will give you grams of magnesium. You do the same thing for oxygen, and remember, oxygen gas is not the 16. Common mistake students make is just assuming that oxygen is O. They would use here 16 instead of 32 is diatomic. You'll end up with the wrong value and you'll make the wrong conclusion. So here are the root mass. And if you look at the mass of magnesium oxide, if magnesium is our limiting reagent, this is the number of moles, 1.74. And if you see these underlines, means our last significant figure, because of the three significant figures, 1.75, I'll say 1.75. Whereas for oxygen, 2.11. Clearly, even though this one is present in small amount, it turns out that it is the excess reagent. Look at how many moles we expect if all these 33.8 grams of oxygen are consumed. So this is our limiting reagent. And if you look, it's present in excess, not excess, but in large amount with respect to the mass for the 2.5, 33.8. Somebody may assume that this is less and it's limiting reagent. No, do the calculation. The one which gives you less amount is the limiting reagent. And if you look at the mass, 70.5, because of what? Because of the three significant molar mass. So this is the grams of magnesium oxide you expect when you react 42.5 grams of magnesium with that 3.8 grams of oxygen. All limiting reagent problem follow the same format. All you have to do is you have to be careful. You should know how to set up your calculation, which one will be your denominator, and use the unit so that when you cancel, you know what you are looking. Don't just put numbers and, without knowing which one. You have to cancel the units the way you cancel the numbers. This is just another example. You can go through on your own how to figure it out, the limiting reagent when carbon monoxide react with hydrogen gas to form methanol. This is a methanol, all right? In the same way, you can just proceed with the setup, figure it out which one is the limiting reagent. And you can be asked how many excess reagent will be left over. If it is in terms of moles, you have to change the moles to grams. Thus, there will be 4 moles of CO2 consumed and 1 mole left over. This means left over 5 minus 1. So if I want to change to grams, it will be 1 times 28, I believe 28, 12.01 plus 16 is 28.01. That is the molar mass of CO. So in terms of moles, this is the number of moles it will remain. You can change to grams. I don't want to spend time just walking you through this. Please spend some time go through how to determine the limiting reagent, the excess reagent, the mass, especially when you're dealing with mass to mass, all right? Except when you're dealing mass to mass, you need to look at the chemical formulas, use the correct formula. So for this is how you'll proceed with the setup. Be careful with the mole ratio, all right, so that you end up with the correct answer. So for A, these are the number of moles of citric acid required to react with sodium bicarbonate. You'll be given that. So you can do this follow to see how much you will end up with to neutralize that. This is another example apart from that. It's going to show you how to proceed in determining the limiting or percent yield. For that, here, aspirin, acetylene salicylic acid, is produced by reaction of salicylic acid and acetic anhydride according to the following reaction. Okay, in a certain aspirin synthesis, 104.8 grams of salicylic acid and 110.9 grams of acetic anhydride are consumed. Calculate the percent yield if the reaction if 105.6 grams of aspirin is produced. Here, this last statement here, this number, this is the actual yield. This is the actual yield. From the statement here, you need to figure out which one is the limiting reagent and the theoretical yield, because for percent yield, we need to have actual, which is this value, 105.6, over the theoretical, which you will have to determine from the given masses of each. So you need to balance this equation. If not, you need to balance that. And from the first reagent, this is the moles we have. This is the moles we have. Salicylic acid is the limiting reagent. And you know which one is which? You know, C4, salicylic acid, C7, this is acetic anhydride, salicylic acid. So salicylic acid, change to grams, change to moles, and what you will see or take note is this is the number of moles. How do you know that this is the limiting reagent? It's based on, it is, you see carbon here, 4 plus 7 is 11. So 9 plus 2 is 11. So 11. In other words, the equation is balanced. Let's see hydrogen. 6 plus 6 is 12. So 8 plus 4 is 12. So 1 to 1. Ratio here is 1 to 1. And that is why we are saying here, if we're starting with this and we're starting with this, mole ratio is 1 to 1. This is the limiting reagent. This is the limiting reagent. And this will be the number of moles of the desired product, which we can use the molar mass to find the theoretical yield. 0.7588 moles of the desired product aspirin. This is the molar mass. This is the gram. So if you look at this, why are we saying that this is? Because the mole ratio is 1, which means the limiting reagent is salicylic acid right here. So salicylic acid is the limiting reagent, which will be the same number of moles of acetic acetylsalicylic acid, which is the aspirin, the same number of moles. We use the same number of moles to find the molar mass. The mass produced. This is the theoretical yield, and to get the percent yield, actual over theoretical times 100, which is 77.25. This is a good example, good practice for mass to mass, if you want to call it. Please look at problem 43, 45, 47, 49, 51 on page 162 to practice on the percent yield. Once you know the concept, you're good to go. I know in Alex, you'll have several problems on calculating the percent yield, calculating the theoretical yield. Fast forward 4.5, 3 examples of chemical reaction. All right, let me just minimize this so that I can highlight also types of reaction you should be careful or you should read on. One, here is, you should see, say types of, let me say types of chemical reaction. There is a combination. You need to read that. Combination reaction. There is a decomposition. Reaction two. There is single replacement reaction. There is a double replacement reaction. There is acid base. You may want to call it acid base neutralization. Combustion, which is burning in oxygen. What number was that? That is 6. 7. Redox reaction, which we will talk. Redox reaction, which we're gonna talk about in the next chapter. There is a redox reaction, yes, redox reaction, single replacement, double replacement, and so forth. You can make your own notes on all these type of reactions, all right? It will help you in the future, but for now, 4.5, there are 3 types of reaction. Combustion, which is one of the experiments you will do in Chem Chem 1 lab. Combustion, burning magnesium in air to form magnesium oxide. And alkali metals, these are group 1 metals, and halogens, group 7 elements. All right, let's see. Combustion reaction is a reaction in which a substance burns in presence of oxygen. It is burning in oxygen, and in particular, looking at the combustion of hydrocarbon to form H2O and gaseous CO2. H2O and gaseous CO2 equation is balanced. And if you look at the product of combustion of hydrocarbon, produces 2 products which you're familiar with, CO2 and what? And liquid H2O or just H2O. Combustion, you need to know that hydrocarbon, ethanol, 2, remember from 3.11, section 3.1 in chapter 3, functional group ethanol, 2 carbon chain, and the functional group OH in H2O, in oxygen produce CO2, and liquid H2O produces carbon dioxide and water. So all alcohol produce these 2 products. Just highlighted that. Problem on identifying a chemical reaction, whether it is combustion or alkali metal reaction, determine whether each of the following reaction represent combination reaction, decomposition reaction, or combustion reaction. Well, you need to look at the type of reaction which represent combination. That means two combining one. If I look at this, two are forming one. This is combination reaction. This is oxygen. This is combustion reaction because there is oxygen and the two products you need to focus in combustion of hydrocarbon is liquid H2O and gaseous CO2. This is the decomposition reaction. So remember decomposition reaction, combination reaction, and combustion reaction. So A is combination. A, two or more products combined to form one. In combustion, oxygen is one of the reactant, and the two products in combustion reaction of hydrocarbon or alcohol, in this case, going to be liquid H2 and CO2, and one product breaking down to simpler substances. This is called decomposition reaction. Look at problem number 59 on page 163. That is a good example you can use in practice on the type of reaction on combustion. Let's see, alkali metals, these are group 1, by the way. Recall classes of compound alka, just gonna have this right here, alkali metal. This is group what? Group 1 or 1A, using the Roman numeral, or sometimes it can be just 1 and A is the same thing. Alkali, these are group 1 and you should know what they are. Hydrogen is not one of them, so we have lithium, we have sodium, we have potassium, all right, rubidium, and then cesium. There is cesium at the end. You need to know those are the alkali, not alkaline earth metal, so group 1. If you look at the general, all right, this is an example, but if you look at the general format, balancing the equation for group 1, it's metal hydroxide plus hydrogen gas. So it's an hydroxide of a metal, and gaseous hydrogen gas is produced. Very reactive, very reactive. If you look at the reaction, this is lithium, this is sodium, this is potassium, they are all group 1, and they produce hydrogen gas, Let's see a good example on reaction between alkali group 1. Write a balanced chemical reaction of solid potassium with liquid H2O. So alkali, this is K, solid, plus liquid H2O, so H2O. And again, look at naming and writing the correct formula so that you balance the equation. Remember, it produces potassium hydroxide plus hydrogen gas. It is a metal with an hydroxide, or the metal 1. The next now is balance. Write a balance. Every time you see write a balance, that means you have to balance. So here we have two hydrogens, plus 1 is 3. We have 2 on this side. So if I put a 2 in front of potassium hydroxide, this is potassium hydroxide, liquid H2O. 2 hydrogens plus 2 is 4, so I need a 2 in front of H2O. So I read this as what here is 2 hydrogens. 2 hydrogens plus 2 is 4, so hydrogens. But now oxygen, let's see oxygen. Oxygen here is 2, but here we have 2 plus 1 is 3. Let's put a 2 here. If I put a 2 here using trial and error, so I have here what? 2 times 2 is 4, 6. So if I put a 3 there, let's try 3. So that's 6 plus 4 plus 2 is 6. So this is 3, and there's gonna be 4 here. 3 oxygens. Here I have 2 plus 2 is 4. So if I have 2 plus 2 is 4, we need to balance the potassium. We have 2 there, so we need to balance out the hydrogen. So if I use this, and let's say it doesn't work for that hydroxide, and no, it wasn't. This is why it's not working. It's because of one of the product is hydrogen gas. So this is what I was missing. It doesn't produce H2O. That's what you need to pay attention that they produce hydrogen gas in H2O, but for non-metal, it produces the ionic compound, but for in liquid H2O, that is what we have. So now let's balance the equation here. So if I have 2, there is 2 here, 2 2 plus 2. So if I have a 2 there, I'll have 2 here, 2. So that 2 times 1 hydrogen is 2 plus 2 is 4. So I need a 2 in front of that, and I need a 2 in front of that. And the equation is balanced. So I have 2 hydrogen. You see these 2 metals, it is solid. 2 liquid H2O, 2 liquid H2O. And then here, the hydroxide is just split. Here has been split, but it's remained the same. So remember, this is what it is. But for metal and a non-metal, alkaline metal, metal and a non-metal, of course, you have to use the crossover rule, all right? The crossover rule. It can be any other non-metal, maybe lithium, and non-metal nitrogen. This is in group 1, this is in group 3, and this will be just Li, all right? And you balance the equation Li, and like that. This is the equation. So if I want to do that, it's gonna be Li 3N, and then this is, by the way, the atomic, all right? The atomic nitrogen gas, the atomic nitrogen gas and lithium. Give you an example of non-metals that it had to do with the group number, so that I write the correct formula for my product, and then you balance the equation. That if I put a 2 there, all right, 2 there, I'll now read this as 6 lithium, 2 nitrogens. I need to put a 6 in front there. Please practice more on metal and a non-metal. Write the correct formula using the crossover rule. That's how I was able to end up with that. It could be any other element on the periodic table. Please use the crossover rule. Look at the periodic table, predict the ionic charge, so that you write the correct formula for non-metal. I mean, reaction between alkali, which in this case is same group. Well, it can be any other group. For H2O, we just looked at that. It can be any other it can be any other alkali, not potassium. Just issue for potassium here. Try problem 61, 63 on page 163. This is reaction between alkali in the group 2. Let's remember, one of the product is hydrogen gas. It's diatomic. Lastly, let's look at the halogens. You know, when you say halogens, there is group 7. By the way, just to show you I know you look at this halide, and then halogens. Fluorine, the atomic fluorine, the atomic bromine, the atomic iodine, the atomic part. This is fluoride. They are negatively charged. They don't mean the same thing. And we are not talking about the halides today, but just to give you a heads up, when we say halides and halogen, they are the halogens. So here, halogens react. All right, let me just have this right here, so that these guys react to, all right, react to form what? You look at the halogens reacting with metals, they form metal halides. Here, please write the correct formula fast before you balance the equation. This is just transition metals. It can be any other metal for that matter. Balance the equation. Halogens, or before we look at halogens and hydrogen, an example on a metal here, it can be group 2, it can be group 1. Let's say group 2. Let's say calcium plus chlorine. Remember, calcium is in group 2, so it has a charge of positive 2. Chloride, so that the correct formula is CaCl2. CaCl2. So what I'll do is write the correct formula here, CaCl2. CaCl2. We need to balance the equation, but it looks like it's balanced. So this is the formula for the reaction between a metal and a metal, a non-metal, in this case halogen. I'm using chlorine. It can be any other group 7. Remember, chlorine is diatomic. Remember what I showed you here for halogens. They are diatomic. When you write the formulas, please use that. I can use any other group, any other metal. Please use periodic table to predict the charge for the metal, so that you write the correct formula using the crossover rule before you balance the equation. Here the equation is balanced: 1 calcium, 1 calcium, 2 chlorine, 2 chlorine. This can be solid, just be specific, solid, gas, and so let's just give you example. Now, halogens can react with hydrogen to form hydrogen halides. All right. I know X here is, group 7. X here is 7. So here, X2 will be fluorine, Cl2, Br2, and then I2. And this is the X2 you see here is what I do have here. X's will just form 1. Let's see, an example is, I could use hydrogen gas plus the others use, let's use fluorine gas. This will be HCl. Here X is chlorine, so it's gonna be X like that. We need to balance the equation. We need a 2 there, and the equation is balanced. It could be hydrogen plus fluorine, which is the atomic. It's gonna be hydrofluoric, it will be fluoric. Aqueous, just give you hydrogen fluoride, solid. Anyway, this is going to be 2, and the equation is balanced. So reaction of halogens with hydrogen gas, I've underlined or bolded the hydrogen, highlight the hydrogen. And then lastly, halogens reaction or reacting with hydrogen interhalogens to form interhalogens as 2. So it can be both of these, it can be any of these, and the chemical formula will just formed in the halogens compound. Crossover rule, you start with the least positive in the halogens. Let's see, learning check, write a balanced equation between solid strontium. So if I look at this, it's strontium, let's see. Strontium, Sr, you have to know the chemical symbols. This is solid, Sr, this is solid, plus iodine gas. This is the atomic. You have to know that S strontium is in group 2, iodide is in group 7. When we use the crossover rule, we'll have S R I to strontium iodide. So I'm just going to have strontium iodide 2. And the way it is, the equation is balanced. The equation is balanced. I'm just writing the equation. Remember iodine gas. Iodine is the atomic. This was in the previous chapter, writing the correct formulas. Iodine is the atomic, strontium is in group 2Sr, so it's going to be positive 2 to write the correct formula here. It's an ionic compound, ionic metal and a non-metal. Hydrogen gas and bromine gas. So hydrogen gas and bromine gas. Remember, hydrogen gas is the atomic plus bromine, the atomic to form hydrogen bromide. Hydrogen bromide. So this is Br2. By the way, this is the atomic 2. And I think the 2 just here balance the equation. 2 hydrogens, 2 hydrogens, 2 bromine, 2 bromine, and the equation is balanced. This is the reaction between hydrogen gas, and gas is diatomic. Bromine gas is diatomic too. This is the balanced equation. Please look at problem number 65 on page 163 for more practice. Other than that, this is just a picture of chlorine, bromine, and iodine.